Hey everyone, so we're coming back now to talk about pages 10 and 11, which deal with the concept of heat of formation. And this is a tricky definition that everybody really needs to get a handle on. So heat of formation is called, or is defined as, the heat released when 1 mole of a substance is formed from its elements in their natural states. Now, our symbol for heat of formation is delta H naught sub F. Okay? Now, these are values that are tabulated in the back of the book, and I will also be posting a handout for you to print that has copies of this information in them. So what we need to get good at is writing a thermochemical equation that represents the heat of formation for these different compounds and substances. So, CH4 gas. I'll put my arrow here and do CH4 gas. What elements are involved? Carbon, whose natural state is graphite. We'll call that a GR. Some people just put S. I like GR. And hydrogen, H2, which is gaseous. 2 in front of the H2. Now, it's important to emphasize here that we're talking about the formation of 1 mole of the substance. So this will always, rare occasions, we'll actually be balancing these with fractions. Now for C2h6 gas, it's coming from carbon, which is natural state of graphite, and hydrogen's natural state is H2 gas. But this time I need to put a 2 here and a 3 there for it to work. Now if I were to go into the back of the book and start looking at the thermochemical tables, I'd see that the delta H naught for this is basically negative 74.87 kilojoules per mole. And what that means is that when these elements come together and form this, heat is released. And we can translate that for us as this compound is more stable together than the elements are when they're apart. And that's why this compound forms. It's a stability issue. And the delta H naught for this reaction is negative 84.62 kilojoules per mole. And that's per 1 mole of the product. Okay, same basic thing here. Energy is released when C2H6 forms, so it is more stable together than when apart. Now, C2h5oh Liquid. What we're going to see here is 3 elements involved. Carbon graphite plus H2 gas and some O2 gas. So I need 2 graphites. 5 plus 1 is 6, so I need 3 on the H2. But since I only need 1 oxygen, it's going to be 1/2 O2 gas. And I could look up what that value is. I don't remember that one, sorry. Okay, those are very typical. You're going to need to be able to do these for the test and for other types of problems in this chapter. Now, we could do it even for carbon gas. Your first thought is, wait a minute, that's natural state? No. Carbon's natural state is the solid, called graphite. To turn it into the gas, that is sublimation. Now this is one I do happen to remember. Delta H naught for this is about 718 kilojoules per mole. Now since this is endothermic, this is a positive number, that actually makes sense to me, because to sublime graphite would require a lot of energy, and that's a pretty big number. Now for magnesium oxide, MgO, solid, we would have magnesium, which natural state's a solid, plus 1/2 of O2 gas. That's that heat of formation. For acetic acid, H, C2H5O as a liquid. I'm going to need carbon, graphite. I'm going to need H2 gas, and I'm going to need O2 gas. These are the natural states for those elements. So I got 2 carbons there. On the hydrogens, I've got 3 and 1 is 4, so I'll put a 2 there. I got 2 oxygens, so a 1 in front of that. Now, for H gas, the natural state is H2 gas, so I would actually balance that with a 1/2 in front. Okay? Now, that's breaking a bond. That's actually called a bond energy. And I do remember that this one is about 218 kilojoules per mole. So again, it's got to be endothermic because energy is going in and the delta H value will be a positive number. Now for O gas, I'd take it from 1/2 O2 gas. Again, a bond energy. This one is just around 250 kilojoules per mole. It's a strong bond. It's a double bond. Okay. So for these values that are positive, what's happening is this is actually requiring work to be done for those things to exist in nature. For the ones where they're negative, that energy is being released, okay, more stable together. Now, several of these are actually incredibly important. This reaction, and this reaction, we're going to use quite regularly in the class. This first one will also pop up to us pretty often also. Okay? All right.